Okay, so here we have a classic exam style question which tests the use of these angle addition formulae. So there's no indication that we're going to be using these formulae apart from this clue here. So we've got here a, and we're just going to do part A of this rather than part A and B. So we've got here something that looks a bit like those formulas we've got in front of us on page 6. The cos A minus B formula, well, if I look at the way it's presented, it's a bit confusing, but minus is the bottom sign. So hopefully you can see that cos A minus B would be cos A cos B plus sin A sin B. And A we're calling x, and B we're calling 60. Not minus 60, but 60. So if I substitute those values into that formula, I'm going to end up with a statement that's got some sin x's in it and some cos x's in it, but also some sin 60s and some cos 60s, which I can work out. They give me nice round values when I type them into my calculator. So see if you can use the formula to rewrite cos of x minus 60 using the formula as presented on page 6. And then we've got to somehow turn that into a formula for tan. We're only doing part A of this question. So this is on page 193, question 11. Page 193 in the Pure 2 textbook, question 11.
So in like the tan one, you use plus and then minus for the bottom one. What I mean, like.
So that is just what they're presenting you there is the formula written twice. So the formula that we use is that the cos of A plus B is cos A cos B minus sin A sin B, and the cos of A minus B is cos A cos B plus sin A sin B. And they've just collapsed those and given them to you as one formula written with a rather confusing plus or minus.
So like on the tan one I'd use...
So tan is really confusing, because if it's tan A plus B, you've got plus in one place and minus in another place. Plus on the top and minus on the bottom. Hello.
Good morning.
Good morning.
Good
Good
afternoon.
morning. Good afternoon. I've got student absence, so that's why we're recording. It's facing this way, don't worry. Yes, yeah. These year 13, we can't afford to miss any lessons. So it's, make sure you calculate it in degrees. Now I hope you're comfortable about me writing cos x times a half as a half cos x, and sin x times root 3 over 2 as root 3 over 2 sin x. That's just me being me and liking things to be written the right way round. So I've got to turn this into an expression for tan x. So could anyone suggest a first step? If I want this to say tan x equals, a good first step. I've got a bit of a dog's dinner at the moment in terms of sine x is all over the place and a cos x thrown in the middle. So could anyone suggest a good starting point? Well, I'll tell you what, James, remind me about the relationship between tan and sine and cos, that identity that we...
Yeah, so sine theta over cos theta.
Right, okay. So what I'm looking for is somehow rearranging this so it says sine x over cos x, because I know I can replace that with tan x. The trouble is at the moment I've got sine x twice in my equation. So this is where I get to use one of my favourite maths techniques. So I'm going to collect everything with a sine x on one side. Okay? So at the moment, I've got this here, I'm going to put them both on the same side. Doesn't matter which way around, I'm going to take that away. So it's going to appear on this side. And here's my favourite maths trick. Well, no, it's not my favourite. It's one of my favourites. Grace, what am I about to do? If I factorise the left-hand side, all of a sudden 2 sine x's become 1 sine x. The hairs are standing up on the back of my neck. It's such a good trick, isn't it? Such a good trick. Actually, do you know what? Sorry. Do you know what? I'm going to rewind one step. Because there's something else you know about me, isn't there? Before I factorise, can anyone predict what am I going to do, Lily? Kill a fraction. Yeah, double everything. So, yeah, that just makes it all a little bit easier to deal with. And then we'll factorise, yeah. And do you feel that proof relief flooding over you? Because this is what we're aiming for. And all of a sudden I've got a 4 minus root 3 in there, so I'm thinking, oh, that's looking good. So Beth, what would the next step be?
Could you do where it's sin over cos, is it cos over sin equals tan?
Yeah, so what am I going to do to that equation? Sine over cos is tan, so what am I going to do to that equation?
Divide by cos.
Brilliant. Divide both sides by cos, and which leaves me with a 1 there, not nothing, a 1. And are we happy if at the same time I divide by 4 minus root 3? Which I could put in brackets, or I could leave as it is. So we've got too bright, Charlie, because this will make you feel better. Here's your brand new electric keyring fob. There you go. And I'm not saying I have favourites, but I did notice that Matt Newell's wearing his round his neck today, so there you go. Oh, and on your lanyard. There you go. Excellent. How to get in line. How to improve your predicted grade by at least 1. That's the way to do it. Okay. So, you know, if we sat here and came and did every single type of question that uses the cos A plus B or the sin A plus B formula that I've ever seen, we'd be here for months, all right? So all we can do really is start to get used to the sort of questions that come up. So that's a good example. And you've got a proof, a proof, which goes on to a solve. And you may remember that from the reciprocal identities. We often have these proof and solve questions. We're not going to do the solve today. So have a look at this question. This is question 13 on the same page. Now you may remember on Friday we revisited a technique. Doesn't relate to this question. But we revisited a technique where they said, okay, an angle is acute and sine x is something. So it might have been, I don't know, 5 over 13. And we needed to work out what cos x was. And it's tempting to do shift sine of 5 over 13 and then just cos the angle that you get, which gives you the right answer, so you can always check it. But no, we're supposed to use the identity and say, okay, if that's sine x, then sine squared is just that squared. So cos squared x is 1 minus that, which is 144 over 169. So that means that cos x is the square root of that, which would be 12 over 13. And I'd normally write plus or minus, but because I was told the angle was acute between 0 and 90, I know that all three, sine, cos and tan, are positive, so it's only positive. And once I know sine x and cos x, I can do that divided by that to get tan x. So that was a technique that we did cover last year, and I reminded you of on Friday. Now here we've got a modification of that, because in this question, we're told that alpha is acute and tan alpha is 3/4. And we're asked to, we need to expand a sine a plus b and a cos a plus b, which I know is going to give me some sine thetas and some cos thetas. Well, that's all right, because I've got that in my answer. But some sine alphas and some cos alphas, which are not in my answer, so I need to work those out. So I need a technique here for working out what sine and cos are if I know what tan is. Now, there is a tricky way of doing it using the reciprocal identity. We use the cot-cosec reciprocal identity. But there's an easy way of doing it if we know that the angle is acute. If I know the angle is acute, it could be an angle in a right angled triangle. So it could be that. And I know that in that right angled triangle, the tan of that angle is the opposite side divided by the adjacent side. So I know that in that triangle, that divided by that will be 3/4. Now there's lots of different measurements which would give me 3/4 as an answer, but this is a really simple one. So that's a possible triangle which has an alpha angle whose tan is 3/4. Now I know now I can easily work out the hypotenuse, Pythagoras, and write down what sine alpha and cos alpha are. So this is a nice trick we can use if we know what the tan is. We don't have to use any identities. We can just use some good old-fashioned SOHCAHTOA. So go on, see if you can work out what sine alpha and cos alpha are, given that tan alpha is 3/4. Then we've got to solve this. So we're going to use the sine a plus b formula and the cos a plus b formula. Once I've used that, I'm going to multiply everything in my answer by 3. And once I've done that, I'm going to multiply everything in my answer by 4. Then I'm going to cross my fingers and hope that when I add it all together, it gives me 5 lots of cos theta. I'm a little bit worried about the sine thetas, but I'm going to cross my fingers and hope it sorts itself out. We're not going to do part B. So these formulas, Charlie, we don't have to derive them at all. There is a sort of proof that we are expected to be familiar with, but we haven't looked at that yet. They're just given to us on the formula sheet. Sorry, it's a dreadful thing to do. A is theta, B is alpha. You're going to use the two formulas from the formula sheet. And we know what sine theta and sine alpha and cos alpha are.
You've definitely lost me somewhere.
Right. Did I lose you here?
Yeah.
So what's that length? Pythagoras.
H.
Yeah, but how do I work out the length of that?
That squared, that squared.
Yeah, it's 5.
Okay.
Okay?
And then I'm just doing like O over H over.
That's right. So
Okay.
sine is O over H, and cos is 4 is A over H.
Yeah.
And I can only draw that because I'm told that alpha is acute. If it said alpha was obtuse, then it wouldn't be a right angle triangle, because you can't have an angle of more than 90 in a right angle triangle. And you can use, actually, if a question says, alpha is acute and sine is this, you could use it for that as well. I just think the identity approach is a sort of one size fits all that I prefer. So I need you to be comfortable with the whole plus minus thing. So if you're doing sine A plus B, that's the top sign, so you've got a plus between the sine A cos B and the cos A sine B. And if you're doing cos A plus B, that's got to have a minus between the two terms. So sine theta plus alpha is sine theta cos alpha plus cos theta sine alpha. I know what cos alpha and sine alpha are, 4/5 and 3/5. So that's what I get for that. 3 times that, well, 3 lots of 4/5 is 12/5, and 3 lots of 3/5 is 9/5. I'm going to do a similar thing for the cos, and then hope when I add them both together, I end up with 5 cos theta. So it does end quite happily, because I use the cos A plus B formula, making A equal to theta and B equaling alpha, which gives me that. I've previously worked out what sine alpha and cos alpha are, so I replace that with 4/5 and that with 3/5, writing it at the front. I hope we're okay with that. Actually, I wanted 4 lots of that, because the question wants me to use 4 lots of that, so I multiplied it by 4. That gave me 16/5 cos theta, 12/5 of sine theta. And now we're told to add the two things together. So I'm going to add this to this. And that's really good news, isn't it? Because it gives me 12/5 of sine theta, take away 12/5 of sine theta, no sine thetas. And it gives me 9/5 of cos theta plus 16/5 of cos theta, which is 25/5 of cos theta, aka 5 cos theta is required. So we've got a question here again where there's no mention of the angle addition formula. So we're expected to sort of look at this and think, ah, right, page 6, that's where I look. At the same time, we're expected to realise that being given tan, we're expected to work out sine and cos. I guess if you didn't realise that to start with, you would realise it once you'd used the formula to write those out, because you'd realise the answer doesn't have any alphas in it, so we've got to substitute those. We're not going to do part B. So there's a couple of examples of use of the sine A plus B, cos A plus B, sine A minus B, cos A minus B, and there's a tan version as well. We haven't used the tan at all, but it's there on the formula sheet. And this crops up regularly. It crops up regularly. It's not an uncommon thing. However, by far the most common use of the angle addition formula is what happens when we make A and B both equal to the same angle. And that gives us double angle formulae, which are much, much more useful. This is all a little bit odd, because why do I need a formula for sine A plus B? I've got a calculator which does it for me. But actually the double angle formulae are really useful in solving problems. So we're going to move from the angle addition formula to the double angle formulae. That's the plural. And what I'd like you to do is take the sine A plus B formula from the formula book, page 6 in the formula book. I'd like you to make A and B both x. Which gives us a formula for sine of x plus x, or 2x. So I'd like you to write what you get when you take that formula from the formula book and you make A and B both equal to x. What does it give us? What does it give us? So you get something like that. What can you tell me, Pat, about cos x multiplied by sin x and sin x multiplied by cos x?
Does it equal 1?
Doesn't equal 1, but it's certainly the same thing, isn't it? We've got two lots of the same thing. So we write it like this. And that is the latest identity that we're expected to be able to use. That the sine of 2x is equal to 2 times the sine of x times the cos of x. So if I know the sine of this angle, I can work out what the sine of double that angle is. It's not just double the sine of the angle, it's 2 times the sine of the angle multiplied by the cos of the angle. Now, do I need to remember that? No, because that's in the formula book. You may choose to. You may find that you do it so often that you do remember it, but you don't need to remember it because it's always derivable from the formula book. But that's our latest identity. We only have 3 more identities to go. Can you do the same for cos a plus b? Make a and b both x. See what we get. There you go. So I'm hoping you've got cos x minus sin x sin x. So Jodie, how else can I write cos x?
Cos squared x.
Cos squared x, that's right, that's what cos squared x means. It means cos x times itself. Now there's a potential for confusion here. Isabel, why could this potentially be confusing? The fact that cos 2x is cos squared minus sin squared. Where have we got something that looks a little bit like that?
One.
Yeah, cos squared plus sin squared is 1. So this is a different formula. If you know the cos of an angle, and you want to know the cos of double that angle, you can work it out. You need the cos of that angle, square it, take away the sine of that angle, square it. It's not cos squared plus sin squared. That's the second new identity that we are expected to use. Do we need to learn it? Don't need to. We can always derive it. You may choose to learn it. You may find that we do so much of this between now and Christmas that you see it when you close your eyes at night. I don't know. We don't stop there though, because actually that formula is pretty useless. But what we can do is use the identity that Isabel just reminded us of. Sin squared x plus cos squared x is 1, and the 2 associated rearrangements of it. So sin squared is 1 minus cos squared, and cos squared is 1 minus sin squared. We can use that to rewrite this in 2 different ways. In one of the rewritings, we replace cos squared x with 1 minus sin squared x. And that gives us another new identity that only has sines in it, no coses. We've replaced the cos. And in another version, we take sin squared x and replace it with 1 minus cos squared x to get another version that only has coses in it. Oh, thank you. be careful with this one because sine squared x, it's minus that. So you've got to do minus that. So I'd put that in a bracket, minus outside the bracket, and then minus 1 outside the bracket. So replacing cos squared with 1 minus sine squared gives us 1 minus sine squared minus another sine squared. So that's 1 minus 2 sine squared x. So that is the penultimate identity that we are expected to use. Do I need to remember it? No, I can always derive it. You may choose to remember it, you may find you remember it, but you don't have to. And this one, a bit more fiddly because it's cos squared x minus sine squared x, so it's minus that. So I've got a minus 1, but I've also got minus minus, that's plus cos squared x. So that's 2 cos squared x minus 1. And that's the last identity that we need to know. Actually, I'm not telling the truth because we're going to do the tan one as well, but that crops up so rarely that I'm not even willing to consider that as one of the proper identities. So I've got one identity that involves sine 2x. So if I get a prove question, or a solve question, or a prove and solve question where there's a sine 2x, your little spidey senses need to tingle and say, right, that's got to be something to do with this. And if you get a question that involves a cos 2x, well, you need to think, right, that's probably going to either involve this identity, rarely does, this identity, or this identity. How do you know which one? Well, maybe it's an equation where everything else is in sine. So it's probably going to involve that. You might end up with a quadratic in sine. Maybe it's an equation where everything's in cos. And certainly my job between now and Christmas is to get you to the point where you are able to choose which of these rules you're going to use in which situation. Let's just do the tan one as well for completeness. So it rarely crops up, but tan a plus b, can you just write what you get if you make a and b both x? The tan formula is complicated, Isabel called it earlier, because you've got, if it's tan a plus b, you've got a plus on top and a minus underneath.
When do you think we'll be finished with the stuff?
Easter, I'm absolutely hoping. It may be that we have to do some stuff on video in order to get that completed. But I'm also hoping in February we will be, the syllabus might be trimmed down a bit when they come. So but yeah, I'm absolutely determined to get through everything by Easter. But we will have started past papers before.
All right.
So that won't be the start of it. Okay, so I get tan x plus tan x, so that's 2 tan x, over 1 minus tan x times tan x, which is tan squared x. So that is an identity. It rarely crops up. So what we can do when I next see you, which is tomorrow? Yes, I see you back tomorrow. You'll get your first go at an I Love Trig sheet, which is a chance to summarise everything. Jodie, you're going to miss out on that. There we go. Them's the breaks. But that'll be the first chance we have to summarise all of these different rules. Let's just dip. Yeah, sorry.
Are you allowed to divide between bottom and tan?
No, because tan x can be 0. And anyway, and I'd have to divide that by tan as well, wouldn't I? So because you've got 3 things, all which so it wouldn't actually help. Good question. Let's just dip our toe into the water then of how we use these identities. All right. So don't be alarmed by what you're about to see. We're just going to do one of these questions. We're going to do part B. Okay. So we're being asked to solve this equation here. It's just part B. So we're not being asked to prove, we're being asked to solve. Sometimes it's prove, sometimes it's solve, sometimes it's prove and solve. Sometimes it's show that, which I sort of count as prove. So there's no mention of that a plus b in brackets or a minus b. It's not like the ones we did at the beginning of the lesson, but there is a cos 2 theta in there, which should set big warning bells going. Cos 2 theta is something I've got identities for. I've got 3 ways of writing it. I've got this way, which involves cos and sine. Never very useful. I've got this way, which is all to do with sine. Well, if I replaced that with 1 minus 2 sine squared theta, I'd have an equation with sine squared and cos. Not very useful at all. We've got a third way, which takes cos 2 theta and writes it in terms of cos squared. Now that's a bit more promising, isn't it? So I'm going to take that and I'm going to rewrite it using the identity. And you're not expected to sort of justify that at all. You can just do that. So I've just replaced, I know it's x here and theta there, but I've just replaced that with that. And, ideally, you'd spot that and make that link. And it may be that you spend 5 minutes at the start of the exam writing the identities down on your formula book. That might be a good way of doing it. Or it might be you wait until you get to the trig question and do it then. So we've got a quadratic equation. So James, what am I going to do to this quadratic equation? What do we always do with quadratics?
I think equal 0.
Line it up, that's right, yep. So if we line it up, whack your calculator into equation mode to get your solutions. They'll be cos theta solutions, and we're asked to solve this in the range minus 180 to plus 180, which is that range there. I'm hoping you spot that that's not a valid solution. Cos can't be less than -1. So I've only got this solution, which my calculator tells me is about 0.78. So I'm expecting, that's about there, to have one solution and then another solution there. So shift cos of that value, and of course it is a pain, isn't it? You've got to come out of equation mode. 2 calculators, perfectly okay if you wanted to. We need to be in degrees on our calculator, worth checking that, isn't it? So, because I've got that funny range of values, we don't often have that, do we? -180 to +180. I've only had to draw half a cos curve there. So the other half of the cos curve is on that side. And so the 2 solutions are nice and easy. So we're going to work our way through most of these questions. Some of them are easier than others. And some involve identities that we've met previously as well as these ones. But yeah, that's what we're heading for. I can help.